Okay, before I launch straight into things, I should just let you know that this is actually the first time I've talked on this topic at all. This is kind of a departure from my usual things. So I'm experimenting on you guys as much as speaking. So I very much appreciate any feedback from any of you or ideas for where we might take this in the future. What I'm going to tell you about is a project with a young Ph.D. student, Armin Saisani, and a fellow with a familiar last name to me, at least, my dad, who is an emeritus professor of psychology in the same department. I like to think he's a professor in my department. He likes to think I'm a professor in his department. But we actually co-supervise on this PhD project, which was great fun, at least for us. I hope it was for Armin. He at least continues to work and publish with us, so I guess we must have gone all right. And this all started when Armin came to talk to us about a question that he had floating around his head, which was how do blind people understand color? And when you think about it, this is a very interesting question. Color is one of those very few sensory properties that has no analog in any other sensory modality, right? It doesn't have any form, any texture, any sound. It's just color. So if you've never had visual experience with the world, how do you understand it? Or do you understand it? I'm going to try and persuade you over the next 45 minutes or so that blind people, at the very least, can develop a pretty rich sense of color. And I'm going to try and explore a little bit about exactly where that comes from. So just to orient you a little bit, at least since Newton, and arguably for half a century or so before him, we've sort of understood colors to be related to one another in a way that we can kind of express as a circle. Newton's color circle is the first real attempt to map colors in this kind of circular arrangement based on their hue. There were previous attempts to express color relationships which included non-hue dimensions, but Newton had this idea that we could represent similarities or relationships between colors around a circle like this by analogy, interestingly enough, to the musical scales of the time, the Dorian musical scale, that he imagined that we should be able to represent color going around a circle, much like musical notes going around an octave, and there should be analogies there. Now, the analogy to music has not really stood the test of time, but the color circle has. The idea that similar colors map next to each other as you go around the circle, and that by the time if you start at red at the long wavelength end of the visible light spectrum and go all the way around to violet, you get back to red again. And this is now so familiar to us that we don't even really question it, right? And it turns out that since Newton, there have been many more attempts or many more variations of this color circle idea, from Herring and opponent process colors, where colors on the opposite sides of the color wheel are in some sense exist in opposition to one another or are coded somehow oppositely to one another, to Munsell in the early 1900s, to more recent iterations in the 1960s, the Scandinavian natural color system, and more modern understandings of color, all kind of represent color in this color circle. So what we're going to look at when we look at blind people today is the degree to which their color understandings mimic that color circle, Newton's color circle, or any of the other iterations that really just shift the relationships between colors a little bit to suit various purposes, whether they're trying to create equal perceptual distances between colors or different representations of colors for different artistic or scientific purposes. They really all have the same general characteristic of representing color in a circle. So our question, as I mentioned, is how do people who are blind, who've never seen color, we'll also look at some people who have seen color but have been completely blind for decades, or people with anomalous color vision, people who are colorblind, and in particular for our purposes, red-green colorblind. How do these people understand color, and can we compare them to normal sighted people with trichromatic vision, with normal color vision. And if they do have something that looks like normal color vision or color understanding, where does it come from? How did it get there? To investigate this, I want to tell you, just segue briefly into the technique that we're going to rely on the most. It's a technique called multidimensional scaling, which was sort of introduced into psychology really by Roger Shepard in the 1960s. It had been around before as a way of sort of representing similarities or distances between objects of some description since the 1950s, but became a sort of tool in psychology for understanding how people conceive of the relationships between things. I'll give you a brief idea how it works. The idea is you start with a similarity or a dissimilarity matrix. So a similarity matrix would be a matrix of how similar things are to one another or how distant they are from one another. A dissimilarity is just the reverse of that, how dissimilar things are, how far away they are from one another. And multidimensional scaling will figure out through mathematics that's more complicated than I care to try and do in front of you, the appropriate number of dimensions that can represent that similarity matrix, and how we can represent the relative positions of the objects that were rated in the minds of the observers who did the ratings. I'll give you a couple of examples that should hopefully make that a little bit clearer. Here's an example of what's called metric multidimensional scaling. The input matrix there on the left, there won't be an exam on the numbers in the matrix. The numbers in that matrix are the air miles distances between the cities that you probably can't see listed there. A number of cities in Europe and Scandinavia, as well as Beijing, serve as the input matrix. When you submit that input matrix to multidimensional scaling, what you produce is can I make the mouse appear on this? I can. What you produce is a map of proximities, of configuration that minimizes or maximizes the variance explained in the proximity matrix, that actually pretty neatly preserves the relationships between those cities on the map. You can the map there just shows the locations of the actual cities on the map, and you can probably see if you were to take that, come on now, if you were to take that configuration and rotate it appropriately and superimpose it on that map, you do a pretty good job. So basically, just starting with the distances between cities, we can reconstruct what the actual distances between those are on a two-dimensional map. Multidimensional scaling will allow you to determine the appropriate number of dimensions to represent that distance, those distances. We can also use multidimensional scaling to get into the heads of observers and ask questions about the psychological distances between psychological concepts. So here's another example where this is now using what's called nonmetric multidimensional scaling, where there isn't an objective distance between items on the list of things to be compared, but instead there's some psychological distance between them. And if we just, instead of submitting the raw distances, we submit something like the rank ordering of those distances, we can ask questions like, how similar are the USA and Cuba by whatever psychological distance you think of, between India and Congo, etc. And this is a map of I think conducted in the 1950s or 60s. So these points may have shifted in time in the meantime, but a sort of a psychological similarity scale for a number of countries. So you can kind of see from that the people who participated in this experiment thought that the USA and China were really pretty different from one another, whereas the USA and Israel and France were all kind of similar. They grouped together on that multidimensional scaling map. And we're going to do something very, very similar with color terms and ask the question, if we just present blind people or sighted people or colorblind people with pairs of color words and ask them to rate them on, in this case, dissimilarity. How dissimilar are they? So if I present to you with red and green, you might say, those are really unlike each other. So I'm going to give that a 7. Whereas if I give you green and blue, you might say, oh, those are a bit more similar, so let's give that a 4. And that's how we're going to do it. We're going to present you with a bunch of color terms, submit that dissimilarity matrix to multidimensional scaling, and see what the internal headspaces of color look like for people who vary in their experience of color vision. It turned out, of course, as soon as you have an idea that sounds interesting, somebody's always done it 40 years before. And this had in fact been tackled in a very similar fashion by Roger Shepard and Lynn Cooper, who did this study while Lynn Cooper was a Ph.D. student of Roger Shepard's in the 1970s at Stanford, and by Gail Marmer at Princeton. They actually both did these studies in 1978. The Shepard and Cooper one was not published until 1992, but inspired the Marmer one. So the Marmer study that came out 14 years before the Shepard and Cooper one was inspired by the Shepard and Cooper one. It's all a bit complicated. So those two studies both asked the same question: do blind people have an understanding of color that's similar to that of sighted people? And they asked people to rate the similarity between pairs of color words chosen from that list I have there: red, orange, gold, yellow, green, turquoise, blue, and violet, with slightly different groups of participants. Shepard and Cooper used sighted people, blind people, and people with various types of color vision anomalies. Marmer was interested in the, actually inspired by Shepard and Cooper, was interested in whether the duration of blindness made any difference, whether people who had fairly recently become blind had some disturbance of color understanding, whereas people who have been blind for a while may be different. Let's see what happened with those. So Shepard and Cooper's answer was that no, people who are blind have a rather distorted sense of color. Let's walk through this slide. The color wheel here, this is the multidimensional scaling solution for normal trichromatic observers, people who were just normal color vision, like I presume most of you and me. And you can see its close resemblance to Newton's color circle, which I've just flipped and rotated to map colors onto colors, but it's a tight resemblance there between the color space that multidimensional scaling produced for normal color vision, and I think that provides a nice sort of validation of multidimensional scaling as producing something that makes sense, right? If it didn't produce something that looked like that, we might worry a little bit about whether that's actually a sensible approach, but it looks really good. And however, the blind observers, 3 blind observers, which sounds a little bit like the sort of nursery rhyme that Roger might have read to his kids. 3 blind observers produced a multidimensional scaling solution that had structure and there's information in there. These are the 3 best of the blind observers they tested, so the 3 who sort of conformed most with the trichromats, but hopefully you can see that it no longer really resembles the color space. There's some separation between warm and cool colors perhaps, but it looks like these people don't have a sort of normal understanding of color as we might go looking for it. Marmer, on the other hand, when she tested larger groups of normal sighted trichromats and people who were early and late blind, so late blind meant they had become blind fairly recently in the last couple of years prior to being tested. Early blind meant either congenitally blind or blind early in life. Hopefully you can see there that all those multidimensional scaling solutions look pretty similar. The blind people in Marmer's study seem to understand color pretty well. So there's a little tension here. There's 2 studies, exactly the same stimulus sets, exactly the same questions asked, produced quite different interpretations of results. So our focus, I guess, shifted a little bit to how do blind people understand color, or do they, to can we resolve a little bit of the discrepancy here and perhaps with the benefit of 40 odd years of hindsight, figure out anything more interesting. Marmer, by the way, also looked at individual differences in her participants. There's an add-on to the multidimensional scaling idea, which is called INDSCAL, or individual differences scaling. What this complicated plot produces is a relative weighting of each participant on the 2 dimensions, and I can't make the mouse appear. There it is. So the idea is that each of these points on this graph represents one of the observers in the study, and it's just asking the question, what's the relative weighting, or the weight on the first dimension, the horizontal dimension, plotted against the weight on the vertical dimension? And if we've done a good job, if we've got a nice color circle coming out of it where both dimensions are expressed fairly strongly, we should wind up with people clustering somewhere up here, good strong weightings on both dimensions. If they're kind of heavily weighted on dimension 1, but not much on dimension 2, they might be down here somewhere. So this person might have a kind of an elongated solution where the first dimension captures a lot of variance, but they're not using the second dimension very much, and vice versa. There's actually a value you can compute from these called weirdness, which reflects the degree to which people deviate from the norm, right? How far do the weights on these 2 dimensions differ from the average of everybody else? So Marma's 3 best participants, these are the 3 participants from the sighted, late blind, and early blind group. In terms of these are the 3 best ones, the ones who correlated with the group mean the best. These are the 3 worst ones. I'd like you to notice that even the worst normal sighted person produces a pretty good color space. The worst of the late blinds looks a little distorted. The lines here between the points are just connecting the colors in order around the color circle. So the fact that they're sort of got a bit distorted here, that corresponds to this point here. So this person is a bit odd, but not really weird, right? This person, where there's really no structure, or the structure of their color space determined by multidimensional scaling looks nothing like the color space that everybody else produces. Oh, what did I do? That person's way down here. That person has very little weighting on either dimension 1 or dimension 2. That the overall group solution is really not doing a good job for that person. That's someone who probably just doesn't understand color. And those data are starting to suggest to me that there's going to be profound individual differences in the blind, and this may, before we even really get going, explain something of what's going on with the congenitally blind. Some people are interested in color. Some blind people are interested in color. They discuss color. They think about it in school. They study color physics or something, and develop an understanding of color. But if you don't have that semantic support, perhaps you wind up like that subject 6 there. If you don't have interest in color because you can't see it, perhaps you don't develop the sense of it. We'll try and work to that as we go. So our version of the experiment, we varied a few things. We started out looking just at people with congenital blindness and adventitious blindness. That is, people who were born blind, have never had any experience of vision or color, or people who became blind a bit later in life. Our adventitiously blind group, or our acquired blind group, are all people who've been blind for at least 5 to 10 years, and in one case 40 years. So they've been blind for a while, but they have had experience of color at some point. And we decided to sort our colors, the colors we would use in the experiment, into those colors we might think of as basic color terms, those that if you have a PC with 8-bit color, you know those color names, and descriptive color terms that are understood as color terms, but also describe something. So turquoise is both a color and it's a mineral, right? So the descriptive color terms we threw into the mix were rose, maroon, copper, orange, saffron, gold, salmon, lilac, turquoise, pearl, cream, and charcoal. So things that all describe something else, but that are colors that we all routinely understand pretty well. Now, I should take pains to point out at this point that, of course, 2/3 of our participants were blind. We're not showing them actual colors. For this whole study, the color terms are just the term. It's all done by reading the color terms to people. Everybody gets it read to them. So the question is about how they understand that concept, not about what it looks like on a piece of cardboard. Because for the blind people, that would have produced nothing very much interesting, I don't think. Yeah. So the colors I put on here are just my interpretations of those colors, and you can criticize my own color space as much as you want, but it's mine and I'm keeping it. So interestingly enough, when we look at the perceptual maps, the color maps of our three groups of participants, are normal sighted, adventitiously blind, and congenitally blind, I think we pretty clearly show that they all produce something that looks pretty much color circle-like. Now, the colors that are outside the circles there are black and white, which we might expect not to sit neatly inside the color circle, because they just don't. But in every case, there's sort of a reasonable progression around the color circle. It looks to me very much like the adventitiously blind and the congenitally blind as groups understand color pretty well. With a little bit more noise around the congenitally blind, but the overall group average here rather suggests pretty good understanding of color, at least for basic color terms. I'm going to show you a couple of sort of individual color spaces. So the color spaces I'll show you for the next 3 slides are individual people's color spaces, not the group average. And I'm going to select 3 congenitally blind people just to show you what the individual differences look like and start to come to some idea what's going on. So I didn't mean that to happen. I meant that to happen. You've all had a preview now. So this participant here, right in the middle, you know what? I'm just going to let the arrow do the trick. The one in the middle of the pack there is kind of the congenitally blind person who looks the most like a sighted person. This is someone who's right in the middle of the pack, just produces the very best color space. And if you look at their actual space there on the left, so we've called that CV4, congenitally blind subject 4, that looks just like a color circle. That's pretty much indistinguishable from the normal sighted people around her. And she turns out to be an interesting person. She's a physics graduate. She's very interested in the physics of electromagnetism. She's thought a lot about color over the course of her life, and she understands it, as you can see there, at least in terms of the limitations of multidimensional scaling, as well as anybody else. That's kind of cool. I've picked out 2 others for having relatively high weirdness values. So the one down here in the bottom right-hand corner, this is somebody who's very strongly weighted on one dimension rather than the other. And hopefully you can see the color space is a bit sort of squished in the vertical dimension. And although there's still some sense of a reasonable color order around the circle, there's clearly a much stronger weighting on that horizontal dimension. And it's a little bit tempting to think that this person is mostly thinking about how bright or dark the colors are. They're sort of ordering them by brightness or something like that. But at least it seems to produce quite an odd color space compared to our sort of beautiful one right in the middle. And this one down here produces just a mess. So this is quite similar in concept to Marmer's subject 6, the sort of worst one. So my take on this, and if you look at the other black dots on this in-scale plot, what I hope you can see is that most of the ones that have fallen off the kind of diagonal there, the negative diagonal, most people are going to fall on that negative diagonal. That's just the way things work. Those who fall off it towards the origin are mostly the congenitally blind. So although the group solution for the congenitally blind is pretty good, individually they don't all do so well. There's some people who have beautiful color images, and some people who have color representations, and some people who don't do so well. And I think this is, again, sort of further evidence that those who kind of get into color, who want to know about it, who take some interest in it, are able to develop a color understanding, but it may not necessarily be the general case, right? That people who, if you sort of look across all the congenitally blind of all the world, you find that some people understand color and some don't, and it depends on their understanding of it. And that begins, I think, to resolve the Marmer versus Shepard discrepancy, because Shepard and Cooper only tested 6 people. They may well just not have picked anybody who was particularly interested in color. Our descriptive color terms are a bit more all over the map, but I think there's still some quite interesting patterns there. There's a general sense of similarity between the congenitally blind and the normally sighted, with a bit more variation. There's saffron, for instance, seems to go into somewhat different places, as does salmon. But the group maps look fairly similar to one another. It has to be said that for both groups, there's much more variability here. There's a fair amount of difference in how people understand things, like perhaps saffron is one of those. I was talking to Chris earlier, and he asked me, by saffron, do you mean the really intense color of the strands, or do you mean like saffron-colored rice? And we didn't specify. We let them have their own interpretation of that. So there's perhaps understandably more variability, because there's more variability in sighted people as well. But I presented this mostly to show you that when we look at the n-scales again, the very same people, the very same 3 cases wind up in the very same places. So the people who didn't understand color very well when we use basic color terms don't understand color very well when we use descriptive ones. And perhaps more interestingly, those who understood color very well when using the basic color terms also understood things about the color of saffron and rose and pearl and cream, etc., and produced spaces that look very much like the trichromatic ones, or the normal sighted ones. That is, that understanding of color generalized beyond just knowing something about the basic colors and the basic color circle. They had a richer understanding of color than just, oh, I know that red's similar to orange because I know the order of colors around the circle. They know more about it. So this just really summarizes what I've just said, that the congenitally blind, I think, are not predestined to have a sophisticated understanding of color, but they're perfectly capable of getting it. And that raises a bit of an interesting question, which I'll return to in the last bit of the talk, of how it got there. It didn't come in through the eyes, so the only thing I can think of is it must have come in through semantics, through interaction with the semantics of the world. And I'll try and convince you of that towards the end. But I want to shift gears slightly for a second and just turn to the other group that we studied, which is people with red-green colorblindness. In the parlance of the field, these are so-called protans and deutans, people who lack either the long wavelength or medium wavelength cones in the eye, and therefore are unable to discriminate between reds and greens and oranges and yellows, that long wavelength end of the spectrum. So they're not colorblind completely, they have anomalous color vision, that all those long wavelength colors are hard to discriminate. Now, this also gives us a chance to do another reality check on multidimensional scaling. We're going to steal and modify the technique used by Shepard and Cooper. What they did is to present the color terms both as just spoken words and as patches of color printed on card. Now we have people who can actually see, so we can give them pieces of card and say, how similar do these things look? We introduced a third condition, which was the color printed on the card, but also with the name printed on the card. So a card that was red that had the word red printed on it. We didn't do Stroop effect. The card actually had the correct name on it, just to see if that provided any scaffolding or any support for their understanding of color. Now, when Shepard and Cooper did this, they got a result that I find a little bit hard to understand. Actually, they presented their colorblind people, their protans and deutans, or red-green colorblind people, with the same pairs of colors that we talked about before, now on cards. And the result was, when they just saw the color cards, that green shifted from here to here. So green became relatively indistinguishable from red. Now that makes sense. What doesn't make sense is why orange and gold and yellow all spread out in the same way they did in the first place. They were just as distinguishable from each other by a visual system that shouldn't be able to do that. So I don't know what happened there. I find that hard to explain. It really should have been the case that if they're just relying on, no, come on now. If they're just relying on the printed colors, all of these colors on this side of the color wheel should have all kind of come together. They should have been hard to distinguish. However, when they gave the colorblind people the names instead of the printed cards, hopefully you can see that the color circle was recreated. That's the bottom right figures there. Their color understanding looks just like normal trichromatic observers, but they can't. So they understand colors they can't see perfectly well. When we did this, I think our data make much more sense. So this is the Hue-Only task. This is the Hue-Only condition, which means we just gave them cards with the colors printed on them. And what I hope you can see is that everything sort of squishes down to one-dimensional. There's more or less a one-dimensional solution to the color similarity, with a little bit of variation on that second dimension. I think can be accounted for by the fact that we didn't control the printing of the cards for luminance. So there's still, the green card is still distinguishable from the red one, not in being different in hue, but being different in brightness or lightness. Yeah. But well, hopefully what you can see is that red, orange, yellow, and green all cluster together there. They're all very close to each other on that plot, whereas our normal trichromats produce normal color wheels as predicted. When we gave them a little bit of support, printed the name on the card, watch what happens. So keep your eyes on the left there. As we give them a bit more support, it starts to spread out a bit. It starts to look a little bit more like the color circle, but not quite. Still squished in one dimension, but they're starting to spread out. So there's kind of like they see the red and green color patches as being very similar, but one says red on it and one says green on it. So they kind of know, okay, those are different. I know they are. I'm going to give that a higher value, and it just went spread out a wee bit. When we just give them the word with no color support, we get a normal color wheel. So they understand color perfectly well. They just can't see it, or they can't see the long wavelength colors. And I really love this bit. This is the in-scales for those same participants. And what I hope you can see, it's not popping out as well as I hoped it might on the screen, but what I hope you can see is that for the Hue-Only task, everything looks heavily weighted towards being one-dimensional. The first dimension is capturing the most. As you give them a little bit more support, they begin to spread out into the normal trichromats, and by the time we give them just the color terms, the in-scales overlap completely. So you can sort of see that spread through the trichromats as you give the colorblind some support. So I won't bother reading all that stuff out. I think you've got the general idea. I want to come back for the end of the talk to the question of color semantics and its influence on the congenitally blind. So I told you I think that the way our congenitally blind participants understand color is by the semantic interaction with the world, by hearing metaphors, by being on occasion green with jealousy and yellow with cowardice and red with anger, and knowing that the sky is blue and the grass is green and that is recycling. And that if you have enough exposure to those kind of things, perhaps over time you begin to develop an understanding of color through its semantics and its use in language. So to investigate the idea, we want to just find, is there some other task, some other way we can link the semantics of color to the performance on, or the creation of these multidimensional scaling spaces? So we dug up an old task and adapted it for our own purposes called the semantic differential. This is a task that's been around since the 50s, and as far as I can tell, hasn't been used much since the 50s, but maybe it has a little bit more than I know about. 60s, 70s, I guess. So what we're going to ask people to do, this looks completely weird, is to is to place each color of the same color terms we used before, the basic color terms, somewhere on the 7-point scale of all these 17 different scales that might have some relationship to color. So some have a pretty obvious relationship to color, hot and cold. Blue is cold, yeah? Red is hot. But a whole slew of other ones too that may not have an obvious association with color unless you think about it hard. Clean and dirty, well, maybe that's kind of obvious. Fresh and stale, calm and angry, happy and sad. I said sad and hard, but it's meant to say soft and hard. Light and heavy, ripe and unripe, new and old, submissive and aggressive, exciting and dull, relaxed and tense, alive and dead, selfless and jealous, fast and slow, active and passive, and like and dislike. So what we're going to wind up creating here is for every one of those scales a kind of a color profile. It's going to look something like these. So we generate 17 of those for the sighted and 17 of those for the blind, and we're going to ask how similar and different they are from each other, and whether they can account for anything interesting about how well our blind people understand color. So if we look at the left-hand column there for a moment, you can see that hot-cold color profile looks really, really similar for the blind group and for the sighted group. Everybody has kind of the same general idea which colors are hot and which colors are cold, and there's not much disagreement between the groups. That general pattern was pretty much true for a number of those color dimensions, or those dimensions, semantic dimensions: ripe and unripe, new and old, submissive, aggressive, selfless and jealous, like and dislike, and active and passive. People generally agreed, or the groups of participants generally agreed amongst each other about which colors went where. Now there was quite a bit of variability. Hot and cold was the sort of the paradigm case that I had to show you as the very best one. But of course, things like and dislike had quite a lot more noise around them. But there was no sense that the blind people did it differently, right? The blind and sighted sort of had the same general profile as one another. There were some where there was things got a bit more subtle. The clean and dirty, say, where there's some general agreements in part of the spectrum and disagreement in other parts, where they produce somewhat different profiles with some agreement and some disagreement. Those included clean and dirty, but also fresh and stale, calm and angry, happy and sad, exciting and dull. And where there were differences between the groups on those, it tended to be the case that the people who had normal vision tended to produce quite spiky profiles. The people who were blind tended to produce, they may agree on a particular color, and then the rest of the spectrum was kind of a little bit muted or something like that. They agreed to a degree, but they didn't agree everywhere. And there are some, as you can see on the right-hand side there, like fast and slow, where the sighted had some semantic association, but the blind really didn't. They just, as a group, didn't have any particular association between color and speed. I guess they don't drive red Ferraris if you're congenitally blind, so you don't get that sense. But and there were a few scales that went like that. So that's all sort of interesting, and we could make the case, I guess, that those scales where there's general agreement between blind and sighted perhaps might give us a hint about which kinds of color metaphors, which kinds of color semantics might be shaping color understanding. But we decided that an interesting way to look at these data, and I welcome any suggestions for how to do this better, was to sort of create for each blind person a measure of sighted likeness. Does that mean anything? I just made that word up. But the idea was we'd take for each person a distance to the average of the trichromats for each color in each scale and just aggregate them. So that basically if we treat the trichromats, the normal sighted people, as a sort of baseline, we can ask how different each person is at each point in our big semantic matrix and compute a kind of average sighted-like rating for that person. So the more unlike the trichromats they are, the higher that number is going to be. The more like the trichromats they are, like the sighted people they are, the lower that number is going to be. And then we can regress that against the D1 times D2 product from the multidimensional scaling space, and ask the question, is there some relationship between the semantics of color from the semantic differential task and where you fit on this, how much like a normal sighted person am I in my general understanding of color? So if there's a strong relationship here, this pretty strongly suggests that semantics is driving things, right? If there's not a relationship, we should look somewhere else. Maybe it's just in the head. But I'm going to leave you with this amazingly strong relationship. The participants who were the most sighted-like in terms of their semantic differential performance, the people who had sighted person-like understandings of semantic relationships to color, were also those who were the most trichromat-like in a completely different measure, the multidimensional scaling task. Those who didn't understand color in one sense didn't understand it in the other task either. And that accounts for amazingly a little bit over 3/4 of the variance in the data. That's
I understand what you said.
the strongest correlation coefficient I've ever seen in trying to regress things against one another. So I'm going to leave you with that thought that it's looking very much like your sort of semantic engagement with color drives your understanding of color. How am I going for time? Yeah, quite well. I'm going to stop in just a second, but I want to bring the color story, if you'll excuse the terrible pun, full circle, and to suggest that, or to at least raise the question that it seems very likely, given how many different attempts there have been over the years to understand color relationships. But prior to Newton, there were all kinds of ideas about relationships between colors that involved arcs and lines and multifaceted shapes. So it's intuitive to us now because we've been hit with Newton's color circle since we were little kids, and we've seen it when we play with the control panels in our computers and the controls for our TV sets. We all get semantic exposure to color. We all learn about relationships between colors as categories as much as perceptual items, right? So I wonder how much of our sort of understanding of color as normal sighted people is in fact being driven by our semantic involvement with the world. Now, I suppose to some of you that may be old hat, and just as a guy who spends most of his time at the back of the brain in the visual system, I hadn't thought of it before, but I have now, and I'm intrigued what you guys think about this prospect that a lot of our sort of categorical perception of color and of maybe many other things is influenced by our semantics, our metaphors, our similes, our general use of categorical terms and categorical and perceptual terms in describing and discussing the world. So let's leave it at that. I think I'll again skip past the summary and conclusions because I've already summarized and concluded. And just to say thank you all for your attention, and I look forward to some questions.
So what we'll do is we'll take some questions from the room, and then if there's questions in the chat box, we'll deal with those.
Okay, sounds good. Chris has one.
So this reminds me quite a bit of what Rupik Desai, one of the members of our team, he looks at aphasia and problems with speech that are related to motor problems. And so problems with verbs that he thinks have a lot to do with embodiment. And all of the people you work with have lost sight due to what's happened with their eyes. So I wonder, has anyone looked at similar stuff with achromatopsia, where they can't see color because of brain injury, the part of the brain that in healthy people learns color associations and deals with the inputs of the eye? Do you think that would be different?
That's a great question. The question, to paraphrase the sharp end of the question, so I probably can't paraphrase the whole thing, but what might somebody who has cortical achromatopsia rather than peripheral problems who's the part of the brain that kind of makes those associations with color, how might they perform on this? The short answer to the question about whether anyone's looked at that is if they have, I'm not aware of it. But it would be a great population to look at, actually. I think that would be a really interesting question to see if that kind of, if the machinery of color cognition was malfunctioning somehow, would that produce a distorted color space? I'm tempted to think yes, that would be a cool thing to look at. But that's a gigantic speculation in hand wave. I could imagine that going either way, but boy, I'd be interested to know.
Like, I know that Martha Farah had done some stuff with mental imagery and saying that after a chromatopsia they had harder problems with mental imagery. But that's a little bit different than actually the semantic space, whether that's still preserved.
Yeah, that's a great question. So that's pretty interesting.
I was wondering if you had a chance to look at correlations between amount of reading that people do, so readers versus people who don't, and which includes audiobooks. But also very
only informally. So we sort of debriefed all the participants, and it looks informally like those people who are more interested in the kind of the world around them. So including reading, but kind of engaged with study and all those kinds of things, seem like they're the ones who tend to look more like sighted people, and those who seem a bit more disengaged from study and academia and so on seem like they're the weaker ones. But it's very informal at this point. I'd hate to take that too far. Yeah, I'll go over here first.
I was curious to know how actually, especially the participants in the early blind group, they actually describe their perception about color. How did they actually report that to you?
So the question is how did the people in the early blind group sort of describe their experience with color?
And was there actually a difference between like their expression of their experiences compared with the late blind people?
So our group were quite heterogeneous in terms of how long they'd been blind. They all kind of claimed to be able to remember color. We didn't get much of a strong sense of differences between, as a function of how long they'd been blind. Some of them, we had a couple of them were actually quite old and had been blind for 40, 50 years. And they sort of said they had a little bit of trouble with general visual memory. They sort of had the awareness of what things look like seemed to be starting to slip, but it didn't influence their performance in any noticeable way.
So I guess my question was like, did they actually describe their perception in terms of like associating colors with like different objects?
Good question. So the follow-up question is whether they describe their perception as being as colors being associated with particular objects, or was it more amodal or something like that, I guess. I'm not sure. I didn't interview too many of these people myself, so I'm struggling to think of any particular examples of associating with objects with colors, but I suspect that if we pushed them, they probably do. That would be my guess. Great.
So going back to how Newton's color wheels influenced us, I get the feeling from what you presented, you kind of convinced me a lot of this is semantic learning that we get. And your iconic example of hot and cold, mapping from red to blue, even though by your own admission one of the blind people was a physicist, it's completely reverse of actual physics. If you think about it, the Kelvin, blue flames are hotter than red flames, right? And if you think about a bluish light, it's actually a hotter light bulb than a reddish light bulb. And it's interesting that we as a society, we've all chosen red as a hot color, or maybe even psychologically it has some influence, but it seems like all of us have chosen this through semantics. I don't know if this is particular in English, and if there's other languages that do it differently, but you could say objectively, from a physicist's point of view, it's backwards.
That's true. So just to paraphrase a bit of the question, in some sense, the mapping between hot and red and blue and cold, which we and the blind seem to agree on in lockstep, runs counter to actual physics. Right, black body radiation would be the reverse. The blue colors would actually be hotter flames or hotter radiation. but that's not kind of how we encode it. And even the physicist didn't encode things that way. She encoded things much more like the blue is cold, ice is white. And my guess is that just reflects the power of linguistic context as much as anything. And actually may know intellectually that black body radiation works that way, that all the rest of her linguistic experience of the world maps blue onto cold. At a guess, this is all, I'm speculating wildly, I have to say.
Isn't it sort of misleading to put it that way, because it's not necessarily within that domain that the colors are mapped, but across everything that we encounter. So igloos are more blue versus flames, right? So, I mean, and those are things you encounter in the world.
Related to that, I think when we look at any kind of mental representation or field of knowledge, it's never the case that our kind of naive theory of any domain is in line with the scientific theory. So the fact that in physics you get...
Speak for yourself.
Science shows us that. So I think it's pretty easy to see why we associate red with hot and blue with cold, because of the kind of the naive physics theory we have of the world, which I don't think is at all informed by the physics of the and so forth. You know,
but it is
typically when we encounter things in the world, if they're bright, they're hot; if they're darker, they're cold.
But it is sort of interesting that even a physicist has naive physics.
Well, it's,
Yeah.
well that's
That's a common thing in psychology.
Yeah, that's true.
Well, the early physicists, right, had exactly the same physics that we do.
Yeah, true.
They started from there,
Yeah.
and then developed it.
Just a question more on the methodology. So about the dimensions of
Right.
multidimensional scaling. So maybe you can say a little bit more about how the number of dimensions is established. So for example, I was thinking we seem to assume, or you, or in the analyses, the analyses seem to assume that the number of dimensions for the blind participants would have to be the same as that for the sighted participants, but it's theoretically possible that they use different numbers of dimensions, maybe more.
Yeah.
In which case, if you map both of the groups on those same numbers of dimensions, they look a lot more alike.
That's a great question. So the question was about how do we choose the numbers of dimensions for blind and sighted, and the implied assumption in the talk, which I think is fair enough, was that the appropriate number was going to be the same for blind and sighted, and that doesn't have to be the case, right? We could have gone for another number of dimensions, and that might have changed the whole story. So the way you choose dimensions for multidimensional scaling has to do with how much of an improvement in what's called the stress values you get as you add dimensions, and you sort of choose a minimum number of dimensions that satisfies some criterion for how well you've done. So of course adding more dimensions trivially improves your fit, right? If you have, you know, a dimension for everybody, then you fit things perfectly. So it turned out that when we looked at this, that the solutions for the congenitally blind were more stressed than the solutions for the sighted, so that there was some justification for thinking about a third dimension, which we looked at too. We plotted three-dimensional solutions for everybody and tried to see if that made any more sense. And it just kind of did it. The third dimension sort of gave us some improvement in the stress values, but looking at it didn't sort of make any obvious sense for how we might interpret things. And
It's because you're not blind.
because we're not blind. That's true. So I mean, it's entirely possibly the case that a three-dimensional solution would have produced something with a different pattern. Except that I think the real take-home story is one of similarity between the blind and the sighted rather than difference. Had they been massively different, then I would have been much more concerned about whether you appropriately chosen a two-dimensional space. Yeah.
On that point, does that sort of imply that what the blind subjects are doing themselves a multidimensional scaling of the data that they receive. With a, in acquiring language and having these words and trying to figure out the semantics underlying it, they're like, okay, what's the structure in the color terms that I'm getting?
Yeah,
is that the implication?
So the question is, which is a cool, it's a meta question almost, isn't it? Is are the blind doing, in effect, in order to create this sense of color, are they in effect integrating over their lifetime or over some semantic integration window?
Right. Are they trying to simplify the conceptual representations?
Yeah, doing their own internal multidimensional scale, and I suppose the answer has to be something like yes.
Right.
Now, whether it's exactly analogous or just kind of at some higher level similar, I would hesitate to speculate too far, but I think probably yes, that you must be doing something like that to sort of realize over time that oh yeah, I've heard people say that orange is kind of ready, so maybe orange is close to red, and you start to kind of push them together in your semantic space. I think that's probably right.
Right.
Yeah.
So Paul, I mean, I'm assuming you're aware of the whole literature on the Morphian hypothesis.
I am, yeah.
Right. I mean, people, I guess, you looked at languages that differ in their color terms, how they map on the colors, and at least you're almost, I'm guessing you're familiar with that.
Yeah, so the questions was about sort of the Morphian hypothesis and whether, like, I think the implied question might be if you had different sets of color terms and different ways of describing color, might you come up with a different solution? We haven't quite gone that. We had while we were doing this stuff, we had an Argentine student who was studying in Italy come and work with us for a while, and she was very interested in what happens in terms of creating color categories with languages. Like, so Spanish is interesting, right? Some versions of Spanish distinguish between sort of sky blue and navy blue, and some don't. For some it's just blue, and for others there's a sky blue, and so the two kinds of blue are categorically separate colors. So we speculated a lot about what might happen if you in fact had a different kind of color language in your head, but it's all kind of hand-wavy.
Well, there is, I think, already some pretty solid evidence that the language you speak and the specific choices in that language about the color boundaries can affect pretty low-level perceptual decisions. I think there is some debate about that, but there's also apparently some, or possibly some, difference between right and left hemisphere, that the left hemisphere shows the Morphian effect and the right hemisphere doesn't, although I think this was kind of a replication problem issue. But
I hope that's true. I like that.
Yeah, it sounds good.
Yeah, it works for me.
But if you look up, so it's interesting. It's really interesting. Many things are interesting, but so thank you. But first of all, your use of the word semantics and kind of the concepts that you kind of refer to under semantics, which I gather from your talk, is anything that is not straight perceptual, right?
Well, I suppose it actually is. So the question was, and I knew this was going to happen to me, as I'm venturing for the first time outside my comfort zone in the visual system, I'm using the word semantics to refer to kind of anything that's not perceptual or anything that's driven by presumably linguistic experience of the world. And yes, that is what I mean, but I'm perfectly happy to be steered.
In kind of conceptual research in concepts and semantics, oftentimes people make, although it can be kind of a controversy, make a distinction between semantics as kind of the core, there's also a difference between linguistic semantics and conceptual representation, but ignoring that for a second, so conceptual representations and then that part of our semantic memory that is to do with associations and so forth. And I think the reason why multidimensional scaling and kind of the pairwise comparisons and even more so the semantic differential methods kind of disappeared for many years is because it was believed that they're kind of giving you some measure about something that's inside, but they're not really directly related to any actual constructs in our memory. So, for example, I'm sure you know the kind of the Kahneman-Tversky kind of criticism of similarity-based semantics that basically highlights the importance of features, right? The Cuba. You actually mentioned one of the classic examples. So, but in recent years, there has been a lot of attempt, I think, because of the availability of large corpora and computing power, to really test this idea that maybe a lot of what we consider to be conceptual semantics can be, maybe is the product of, but at least is mirrored the statistics of the language. So I guess when looking at, for example, your last study where you correlate multidimensional scaling and the semantic differential, I kind of would have suspected that it would give you very strong correlation because they're very similar things. They kind of test very similar things, and perhaps a kind of a stronger test of what I think you're trying to see is to look at language, kind of a corpus, a large corpus, like a huge corpus of language, and apply one of those more recent techniques like Riverside Hall model or the Landau semantic. It's used oftentimes in psycholinguistics experiment, kind of measuring semantic similarity.
That sounds like a great idea. As I say, this is venturing outside my usual comfort zone, so I appreciate a suggestion for a new place to go with it. That's cool.
Yeah, but it seems like, someone, a cognitive person that kind of looks at things typically not in the occipital lobe.
Yeah.
It's kind of, yes, of course, like the meanings that we have are shaped by our linguistic experience, like the semantics we have. When you ask me to tell you how similar is something designated by word A to something designated by word B, of course I will rely on my linguistic knowledge, including, especially for words that I encounter a lot, their contexts and everything. So goes well, I think, with what you said, but not as surprising.
Not as surprising as all that. Okay, happy with that.
On that note, we should end the session. Thank you so much.